real aspect. All right, so let's just do a quick recap. Just to kind of get everyone back onto the same page as best we can here. So leading up into the break in the most recent weeks, we were discussing stratified sampling. So the idea here is basically we understand how to collect a simple random sample from a population. So I have a population of, say, size capital N, maybe capital N is 1,000 or it's 5,000 or whatever. We collect a simple random sample, which just means that we are collecting a sample from the population such that all samples have the same probability of being selected. From the simple random sample, we can estimate a population quantity like the mean, the total, or the proportion. And using the derivations that we found for the variance of that estimator under the simple random sampling scheme, we can then bound the estimate and build effectively a confidence interval. And confidence interval construction is something that we have seen far, like before we even started stat 350, right? This is a topic in stat 151. It's this topic in stat 252. Even in stat 26, well, I was going to say in 265, but I don't think that's true. But in 266, you would see derivations of confidence intervals, but that obviously wouldn't apply here because you don't have to have 266. So confidence intervals are something we've seen in the first year stats 151 and the second year stat 252. And we're using the same idea here. So interpretation of the interval. The only difference really is construction of the interval. And in the SRS scheme, the main difference between interval construction is that we have a finite population correction that we apply when the ratio 1 minus little n over capital N is greater than 0.9 or is less than 0.95. Okay, so same idea as what we saw in those introductory courses, but we're adjusting for the fact that we have a fixed population size. After we introduced simple random sampling, we introduced systematic sampling. And systematic sampling was very similar to simple random sampling. It was so similar, in fact, that we actually used the exact same estimates from simple random sampling when we were doing our systematic sampling approaches. The only time we didn't use the SRS estimates was when we used repeated systematic sampling and when we used what was called difference estimation. Those two approaches, the repeated systematic sampling approach and the difference estimation approach, they fell under the umbrella of systematic sampling, and we utilized those when the population was either ordered or periodic. So you might recall that we talked about how the systematic sampling estimator is affected by the characteristics of a population. So we define 3 types of populations: the random, the periodic, and the ordered. And in each case, we discussed how the systematic sampling estimator, or the systematic sampling variance of the estimator would compare to the simple random sampling variance of the estimator. And in the case that the population is random, we can show that the two are equivalent. So that's one of the main reasons why we use the SRS estimators in place of the true systematic sampling estimators. However, when the populations were not random, so they were periodic or ordered, we showed that the variance of the estimator of the population quantity that we're interested in would be either greater or smaller than the corresponding simple random sample variance of the population quantity of interest. Okay, and this is material that would fall under the quiz 2 umbrella. So that would be something you'd want to familiarize yourself with, is the definition of those 3 types of populations and how the variations of the simple random sampling estimator compares to the systematic sampling estimator. All right, after we finished the systematic sampling discussion, we moved into the stratified approach. Now, Again, the goal here is really the same. We want to estimate some population quantity. It could be a mean, it could be a total, or it could be a proportion. And all we're doing is we're taking a different approach to how we collect the information. So in the stratified approach, we're basically just collecting capital H simple random samples. So we have a population that's of interest to us. Say, for example, that population of interest is all Canadian adults. Okay, so we're spread out across our entire country. And now instead of collecting one large simple random sample from the entire population, we're going to collect H or capital H simple random samples from subsets of the population. Most often, we would break the population into geographical regions. And the rationale for this is we want the strata, so these different regions that we sample from, to be as similar as possible within and as different as possible across. And this again would be something that you would want to review before the quiz. So you would want to refresh yourself and be comfortable with the ideal characteristics of the strata that we are trying to collect. Now, once we have divided our population into these strata, we collect the SRS from each strata, and then we build an estimate for the mean, and we bound that estimate. Or we build an estimate for the proportion or an estimate for the total, and we bound it. When we are using stratified sampling, in almost every, when we are using stratified sampling, our estimates are based off of the true strata proportions. Okay, so you can see on the slide here, we have this capital WH. Okay, so we'll think of this as the population strata proportion. So for the estimates of mu and the corresponding variation estimates, we would want to use capital WH. In general, anytime you have population information, you would want to include it. This is would help us refine and give a more, hopefully a better estimate of whatever quantity it is we're interested in estimating. Okay, so on assignment 2, there was a note from the TA that students were getting confused between when to use capital WH and when to use little wh. Little wh and capital WH would only be interchangeable when we are using proportional allocation. Because under proportional allocation, the ratios of the total sample size across each strata would be equivalent to the ratio of the total population size across each strata. In every other situation, you would want to use the population quantities. So in general, it's actually safer to always just utilize the population quantities unless they are not given, because that would always lead to the most refined answer, if you will. Right. So basically, our stratified approach is just a weighted average or a weighted total or a weighted proportion across each of the different strata. All right, before the break, we also talked about we talked about 3 different sample size calculations. The 2 major types were the optimal allocation and the proportional allocation. The other type was sample size calculation when cost varied across each of the different units in the strata. So we can account for cost, but most often we will assume cost is fixed or the same, and our sample size calculations will only be will really just review, will really just be essentially a ratio of the population sizes and the variance of the population for each of the strata. So those are the major components of the calculation. And again, those are 2 things that you want to review: how to compute sample size for a stratified sample and how to allocate sample size for the stratified sample. Okay. All right, so following from that, what we're going to talk about today is Well, we're going to talk about two things today. The first thing is a very short topic, which is choosing the number of strata. So this would be a natural question, I think, from stratified random sampling. So in the situation that you are considering a stratified approach for collecting information, how many strata should you actually decide? So if there aren't clear geographical regions or there aren't clear boundaries that separate the population into different areas or regions, how would we choose how many strata to use? So we're going to talk about one approach for doing that, which is called the cumulative square root of the frequency method. This approach is a fairly simple idea. It's easy to work through, and it provides us with a method for at least evaluating the number of strata that would be considered optimal in a different for a very particular situation. After this approach, we're going to talk about the idea of post-stratification. Post-stratification is also a very, I think, conceptually easy idea to digest. It's basically saying, okay, I started by collecting an SRS. The SRS is giving ratios of a particular feature that are unbalanced. So I want to correct the estimate after I've already collected the simple random sample. So post-stratification basically means apply the stratified estimation approach after you've already collected an SRS from the population. So it's essentially an adjustment to an SRS estimate to try and balance out some feature that wasn't properly collected in the simple random sample. But we'll see examples of that, and we're going to talk about the derivation of the estimates for that in a little bit. Okay, so an example of this cumulative square root of the frequency method. Again, this approach is an approach that we use to determine how many strata we should have for a particular problem. All right, so in the example, we have the following. We wish to investigate the average electricity consumption for 70 homes using a sample size of 23 homes. So we have a population size of 70 and a sample size of 23. How can we best allocate the houses to H equals 3 strata or to H equals 4 strata? All right. So actually, so really in this example, we're not actually going to be like calculating the optimal number of strata, but we're going to be finding how we can at least bound the strata for a particular problem, which, to be fair, is a different illustration than what I had set this up to be. Okay, so what we're doing in this example is finding the bounds or the the split or cut points for the strata. So we're starting with a different number of strata, and we're saying how would we actually separate these. And then I suppose if you actually wanted to compare the output from the strata, we could do that via like a relative efficiency comparison. So something that we'll start to see more examples of, but we have talked about a little bit, is a comparison of the results from, say, the stratified approach to the simple random sampling approach. And this is something that we can do, well, we did it on assignment 2, but this is something we can do by comparing the variations from our estimates. So we could theoretically do the same thing here. If I have 4 strata or 3 strata, and I wanted to compare the estimates that I received from the 4 strata approach or the 3 strata approach, I could do that by comparing the variations, and the smaller variation would imply a more precise estimate, since we know that the estimates are unbiased in that case. Okay, so for this particular example, how can we best allocate the houses into either 3 strata or into 4 strata? Okay, so the first thing that we'll do is we will compute the cumulative frequency. I always put cumulative. And then on step 2, we will divide by the desired number of strata. All right, so you can see from the table that's given on slide 38, we have the calculation of this cumulative frequency method. So we have the different house sizes shown here in the first column. And then here we have the frequency, which would be the number of houses associated with each different strata. So this would be like little n, and I don't want to write subscript h here because these aren't the strata, but these would basically be little n for each of the different house sizes. Okay. Then you can see what we're doing is we're taking the square root of the frequency in the fifth column, or in the fourth column rather. So we have, for example, 12, square root of 12 is 3.46, square root of 22 is 4.69, square root of 15 is 3.87, etc. And then we are summing the squares of those, or we are summing the square of those frequencies. So we have 3.46 plus 4.69 is 8.15. 8.15 plus 3.87 is 12.02. 12.02 plus 3.16 is 15.18. 15.18 plus 2.65 is 17.83. And then 17.83 plus 2 is 19.83. Okay, so on the second step, so step one is completed via the table, right? So we'll just make a note here, completed in the table. Okay, so on step two, we're going to consider two different strata sizes, or two different numbers of strata. So we'd have h is equal to 3, and we would have h is equal to 4. Okay, so we take the cumulative frequency and we divide by the number of strata. Okay, so that would be step two. So we have step one for both, that's going to be consistent. And then on step two, we would have, so if I put a little 2 here, for example, try and be really clear, we would have 19.83 divided by 3, which is equal to 6.61. And then for h is equal to 4, we would have 19.83 divided by 4, which is equal to 4.9575. Okay, now what we do is we take the this value that we have found for each of the divisions in step two, and we use that to define the cutoff points for each of the strata. So for example, we would have so we'd have strata 1, strata 2, and we would have strata 3. Okay, so strata 1, the cutoff is going to be the 6.61. Strata 2, the cutoff is going to be 6.61 plus 6.61. Okay, so that's going to be 13.22. And then strata 3, the cutoff is going to be 6.61 plus 6.61 plus 6.61, which gives the total back. So now what we do is we look at the cumulative frequencies. Just make sure I have that correct. Okay, and we basically just split the cumulative square root of the frequency at those different cutoff levels. So for example, if we consider h equals 3 here, the first cutoff would be right here. The second cutoff would be here, and then the third cutoff takes everything. So the first strata would be less than 600. The second strata would be 601 to 1500. And then the third strata would be greater than 1500. All right, and then for h is equal to 4, it would be the same idea. So we would actually have 4 strata in this case. All right, so we would start with the first method, or with the first value, which is 4.9575. And then we would add 4.9575 to that number, which obviously I didn't work out, of course. So then we would have 2 times 4.9575. Then we would have 3 times 4.9575. And then that would go up to the total, which is 19.83. Okay, and then if we took h is equal to 4, okay, so our first strata is going to be at the same point. Our second strata is going to be here now. Our third strata is going to be here. And then our last strata will be there. So the results in this case would be less than 600, 601 to 1,000. 1,001 to 2,000. And then we would have greater than 2,000. Okay, so that's the basic idea. So we are taking some splitting feature, which in this case would be the house size. We have the frequencies, so the number of houses that belong to each of those different categories that we have split by. So in this case, again, we split by house size. We have, of the 70 houses in the population, we have the numbers that belong to each of those different house sizes. Excuse me, we take the square root of those frequencies or those sample sizes, and then we sum those values. And then we split based off of the total cumulative square frequency divided by the number of strata. So in this example, we have 2 different illustrations of how we would split that cumulative square root frequency in order to find the split points for the strata when we either have 3 or 4 strata. And then if we were interested in using 5 strata or 6 strata, probably wouldn't be interested in going much higher than 4, but if we were, it would be the same approach, except we would divide by 5, and then we would split according to the cumulative sums from 19.83 over 5 up to 19.83. Okay, all right, so that's our illustration of how to find boundaries for the strata rather than actually how to compute the number of strata, which would have been probably more interesting, but so that's the first topic that I wanted to talk about today. Any questions? Why is it greater than 1,500? Because we have, for strata,
I think it should be both bigger than 2,500.
No, it shouldn't, because strata 3, so strata 1 is taking only what is less than 600. Strata 2 is the values between 601 and 1,500, and strata 3 is everything greater than 1,500. Yeah, like
means the rest of them will be based on the previous.
It has to take all of the information that's left over. And then if we compare that to the 4 strata case, same idea. So the first strata is only going to be less than 600, and then we go 601 to 1,000, and then we go 1,000 to 2,000, and then we take everything else that's left over. So we don't want to leave any information out. We want to stratify or sample from everything that's available to us. So we want to stratify all of the different areas that are available to us. Any other questions? Okay, so the second thing that I want to talk about today, and we'll probably need a bit of Wednesday to finish this up as well, is the idea of post-stratification or stratifying after sampling. So up till this point, the examples that we have seen where we focus on estimation of a population quantity. So the examples where we want to estimate mu, pi, or tau, so mean, proportion, total. We have stratified first, and then within each of the strata, we have collected an SRS. Now, imagine that you have collected an SRS, so you already have one large sample, or you have a sample in front of you. Large is obviously an arbitrary expression. So you've collected an SRS, and then after you collect the SRS, you want to stratify to correct for some feature that is unbalanced in the sample. Okay, so we are collecting first and then applying our stratified approach. That's the basic idea. Okay, so a general example when I talk about this idea of correcting for a feature. Suppose that you collect a simple random sample from a population. You know that the population should be evenly split between the genders, for example. So it should be 50% male, 50% female, which would basically mean that capital WH is 0.5. Right, so keep in mind, capital WH is simply a ratio of the total number of people in the first strata divided by the total number of people in the population. So if you stratify based off of gender, and you know that there should be 50% of each gender, that capital WH should be about 0.5. Okay, so you collect the SRS, you go through and you assess each of the individuals in the SRS. You record the measurement of interest, but you also record the gender, for example. You notice that after you collect the simple random sample, the genders aren't quite even, which you would expect them to be for the population to be representative. So maybe you have like 25% female and 75% male, for example. What we can do is after we collect the estimate, we can split the estimates based off of the gender they belong to. So we can have an estimate for the females and an estimate for the males. But then we can correct those estimates by multiplying by the true population proportions for each gender. So the true strata weight. So the idea is fairly simple. It's basically collect an SRS, note down the features, and then if you observe a feature balance that doesn't align with what the population should look like, you can correct the estimates. Okay, so we can note that this idea or this approach will be nearly as accurate as stratifying before sampling if capital NH, capital N, and little nh are greater than, or given that we know the true values and little nh is greater than 20 for each strata. So the requirements for the accuracy of the two methods to be nearly equivalent is pretty low. Okay. For this post-stratification approach, we now consider little nh, which is the sample size for each strata, to be a random variable. Okay, so we have here let little nh be random because for a fixed n, the values can now change. So then we can write if little n, or we can show that the expected value of little nh, which is now a random value in this post-stratification approach, is going to be equal to little n multiplied by WH, right? Which makes sense. So basically we're saying that the expected value of the number of observations in each strata is equal to the proportional allocation of the sample based off of the true strata proportions. Okay, so for our post-stratification approach, again, from a computational point of view, it's effectively equivalent to what we were doing with regular stratification. The only difference is where these estimates for the mu h come from. So before, we would write that the mu h, well, actually, it's still really the same thing, but before we would stratify, collect a sample from each strata. Now what we are doing is we are collecting one SRS, or we have collected one SRS. We split the SRS into groups. So after we've already collected it, we then break them into separate groups. No, capital WH. Capital. Okay, so we collect the SRS and then we split the SRS into their groups. So we don't actually know how many observations we have from what would be the strata 1 feature and how many observations we have from what would be, say, strata 2 or the strata 3 features. So we collect the SRS, we break it into the different strata, we compute an estimate for the quantity of interest from each of these different portions of the SRS, and then we correct those estimates based off of the true strata weight, so the capital WH. So again, the post-stratification approach in terms of estimation is pretty much exactly the same as regular stratification. The only difference is where the estimates for each strata come from. So in post-stratification, they come from an SRS that is collected first and then broken into groups, rather than from a situation where you collect the, or rather from a situation where you break into groups and then collect the information. Okay. So we're going to go through our usual approaches here. We're basically going to derive the properties of our post-stratification estimator. So for the mean in particular, and then we're going to look at an example. Okay, so we have our usual kind of 2 steps of interest. What are the expected value of the post-stratification estimator? What is the variance of the post-stratification estimator? And then an example of its application, right? And that's pretty much the same thing we've been doing throughout the course and all of the different features that we've looked at. We've defined an estimate. We've defined the properties of the estimate, which are the expected value and the variance. And then we have used those definitions empirically to actually build an estimate and bound that estimate. Okay, for post-stratification, we need to review a few properties from Stat 265. So in particular, if we have 2 random variables, capital X and capital Y, and they have a joint probability function P of X, P of Y, or P of X, Y, we can write the expected value of X as the sum across Y of the sum across X of X times the probability of X conditional on Y times the probability of Y. Okay, so this is just a definition that we are going to use in our derivation of the expected value and for the variance momentarily. So on slide 41, we're simply just reviewing some key definitions that will help us in our derivation of the post-stratification estimate. Okay, now following from this definition, so we can establish that the expected value of X is as it was described and as it's written on slide 41. We can also show that this definition is the expected value of X or we can show that this definition leads to the expected value of x is equal to the sum across y of the conditional expectation of x given y times the probability of y. So that means that the expected value of x is equal to the expected value of x given y. Again, not focused on these derivations in particular. These are just definitions that will help us in our proof for the post-stratification estimator. All right. So let's look at that first one. I think that we'll have enough time just to finish this off, and then we can look at the variance next time. So we will use the definitions from the preceding slides to compute the expected value of mu tilde post. Okay. So again, we're really just focused on doing two things here. Finding the expected value of mu tilde post, which I think most of us will probably realize is going to be mu because it usually works out to be unbiased. And then we are going to find the variance of mu tilde post. Okay. And then once we have the variance, we can use that to bound our estimate, which we defined on the previous slide. Okay. So for post-stratification, we're going to have two random variables in this calculation. So they will be mu tilde post and little n h. Okay, so I'll just write here, start proof. So we're going to have the expected value of mu tilde. Oh, sorry. We're going to mu tilde h and little n h. Sorry. Okay, so we're going to start by using the expected value rule that we defined in the previous slide. So we can write the expected value of mu tilde h is equal to the expected value of the expected value of mu tilde h given little nh equals nh. So we'll call this part one. Okay, and then we can say as long as little nh does not equal 0, we can use the result from simple random sampling to show that the expected value of mu tilde h given little n h equals little n h is equal to mu h. So therefore, the expected value of mu tilde h is equal to the expected value of the expected value of mu tilde h given little nh equals nh is equal to the expected value of mu h, which is equal to mu h. And then we'll call that part 2. Okay, and then we can say it follows that the expected value of mu tilde post is equal to the expected value of the sum from h equals 1 to capital H of WH UH is equal to the sum from little h equals 1 to capital H of WH times the expected value of mu tilde H, right? And then we can see that this is going to be the sum from capital H equals, or little h equals 1 to capital H of WH times mu H, which is equal to mu H. Well, I guess that isn't as expected, but okay. So therefore, the post-stratification estimator is also unbiased for the population mean, which is what we expected, but this is how we could show it's true. Okay, so I'll stop here for today, which means that we'll start with the variation of the post-stratification estimator on Wednesday. Then we'll look at an example of post-stratification, and then we'll talk about another idea, which is called double stratification, and then we'll move on into lecture set 4, which is the ratio and regression estimation approach. All right. Okay, so as always, if you guys have any questions, please let me know. Don't hesitate to ask questions about the materials or the assignments or whatever. Like, I want to help as best that I can. And this should just be a mu. And then just a reminder that we have the quiz next Monday. So please let me know if you need any kind of accommodation for that. And assignment 3 is due March 12th. Okay. All right. So have a good couple of days, and I will talk to you Wednesday morning.